In this video, we will learn about C++ iterators. Iterators are essential tools for working with elements in Standard Template Library, or STL containers. Iterators are objects that point to elements inside a container. They provide a way to access and manipulate data stored within these containers. Iterators allow you to access individual elements within the container, move, or navigate through the container, from one element to another and perform operations on the elements such as reading, modifying, or deleting them. C++ offers several types of iterators, each with its own capabilities. Let's explore some of the commonly used iterator types. First, we have input iterators. Input iterators are used for read-only, forward-moving. They are suitable for single-pass algorithms where you only need to read data from a container once. The operations supported by input iterators are increment, equality, inequality, dereference, and member access. An example of an input iterator is the standard input stream iterator. Next, we have output iterators. Output iterators are used for write-only, forward-moving. Similar to input iterators, they are suitable for single-pass algorithms, but instead of reading, they allow you to write data to a container. The operations supported by output iterators are increment and dereference. An example of an output iterator is the standard output stream iterator. Then we have forward iterators. Forward iterators provide read-write access and allow you to move forward through a container. They support multipass algorithms, meaning you can traverse the container multiple times. The operations supported by forward iterators are increment, equality, inequality, dereference, and member access. An example of a forward iterator is the iterator for a standard forward list. After that, we have bidirectional iterators. Bidirectional iterators offer read-write access and allow you to move both forward and backward through a container. The operations supported by bidirectional iterators are increment, decrement, equality, inequality, dereference, and member access. Examples of bidirectional iterators are the iterators for standard lists and standard maps. Random access iterators are the most powerful type of iterators available in C++. They provide read-write access, allow movement in both directions, and enable you to jump to arbitrary positions within a container. Random access iterators support array-like indexing using square brackets, pointer arithmetic with operators like plus, minus, plus equals, and minus equals, and comparison operators such as less than, greater than, less than or equal to, and greater than or equal to. Standard vectors, standard decks, and standard arrays utilize random access iterators. Here's an example demonstrating the usage of random access iterators with a standard vector of integers. We declare a standard vector named nums and initialize it with some values. We obtain an iterator pointing to the beginning of the vector using the begin function. Now we can perform various random access operations using the iterator. We can access the first element using the dereference operator, retrieve the third element by adding 2 to the iterator and then dereferencing it, and access the fifth element using array-like indexing with the iterator at index 4. We can also move the iterator forward by 3 positions using the plus equals operator, making it point to the element with the value 40. Finally, we can calculate the distance between the current iterator and the beginning of the vector by subtracting the begin iterator from it, which gives us the index of the current element. Now let's explore some commonly used iterator functions in C++. The begin function returns an iterator pointing to the first element of a container. The end function returns an iterator pointing to the position after the last element in the container. The reverse begin function returns a reverse iterator pointing to the last element of the container. The reverse end function returns a reverse iterator pointing to the position before the first element in the container. The constant begin and constant end functions return constant iterators, providing read-only access to the elements. Similarly, the constant reverse begin and constant reverse end functions return constant reverse iterators, also providing read-only access to the elements in reverse order. Iterators are versatile tools that can be used in various ways to manipulate container elements. Now we'll explore some common use cases of iterators. One common usage of iterators is to traverse the elements of a container, allowing you to access each element sequentially. You can also use iterators to access individual elements within a container, either for reading their values or modifying them. Additionally, iterators can be employed to modify elements within a container, enabling you to change their values or properties. Furthermore, iterators are often used in conjunction with algorithms to perform operations on container elements, such as sorting, searching, or transforming data. Here's an example demonstrating the basic usage of iterators with a standard vector of integers. We declare a standard vector named nums and initialize it with some values. We use a for loop along with iterators to traverse the vector and print each element to the console. In another for loop, we use iterators to modify the elements of the vector by multiplying each element by 2. Modern C++ provides a convenient feature called range-based for loops, which simplifies iterating over container elements. These loops use iterators behind the scenes, but with a more concise and readable syntax. Range-based for loops offer a simpler and less error-prone way to iterate over containers, making your code cleaner and easier to understand. They work with any container that provides begin and end functions, allowing you to seamlessly iterate over various data structures. Range-based for loops have been available since C++11, providing a modern and efficient way to traverse container elements. Here's an example demonstrating the usage of range-based for loops with a standard vector of integers. We declare a standard vector named nums and initialize it with some values. We use a range-based for loop to iterate over the vector by value, creating copies of each element and printing them to the console. Then we use another range-based for loop to iterate over the vector by reference, allowing us to modify the original elements by multiplying each element by 2. Finally, we use a range-based for loop to iterate over the vector by constant reference, providing efficient read-only access to the elements. Standard Template Library, or STL algorithms, leverage iterators to operate on containers in a generic and flexible manner. These algorithms are container agnostic, meaning they can work with various container types as long as they provide appropriate iterators. STL algorithms operate on iterator ranges, allowing you to specify the portion of the container you want to process. Most STL algorithms can be found in the algorithm header file, providing a rich set of tools for performing common operations on data structures. By combining iterators with STL algorithms, you can achieve powerful and expressive code for manipulating container elements. Here's an example demonstrating the usage of iterators with STL algorithms. We include the algorithm and vector header files. We declare a standard vector named nums and initialize it with some values. We use the sort algorithm along with iterators to sort the elements of the vector in ascending order. We use the find algorithm along with iterators to search for the element with the value 8 in the vector, storing the result in an iterator named it. We use the transform algorithm along with iterators to apply a transformation function to each element of the vector, multiplying each element by 2. Iterator invalidation occurs when iterators become invalid due to modifications made to the underlying container. This can happen when elements are added or removed from the container, when the container is resized, or when the container is moved or copied. Invalidation rules vary depending on the container type, so it's important to understand the specific rules for each container you're working with. Using invalidated iterators can lead to undefined behavior, such as crashes, data corruption, or unpredictable results. Therefore, it's crucial to be aware of iterator invalidation and take precautions to avoid it. Here's an example illustrating iterator invalidation with a standard vector of integers. We declare a standard vector named nums and initialize it with some values. We obtain an iterator pointing to the element with the value 3. We then call the pushback function to add an element to the end of the vector, which may cause reallocation of the underlying storage. As a result, all existing iterators, including the iterator become invalidated. Attempting to dereference the invalidated iterator results in undefined behavior. To avoid this, we can obtain a new iterator after the modification, ensuring that it points to the correct element. In C++, you have the flexibility to create your own custom iterators to traverse data structures or collections that are not part of the standard template library, or STL. To create a custom iterator, you need to implement the required operations such as increment, dereference, member access, equality, and inequality. Additionally, you need to define the iterator category, which specifies the capabilities of your iterator, such as input, output, forward, bidirectional, or random access. You also need to provide the value type, reference type, pointer type, and difference type for your iterator to ensure proper type handling. It's important to ensure that your custom iterator behaves correctly and adheres to the iterator concepts defined in the C++ standard. You can use iterator traits to provide compatibility with STL algorithms and other iterator-based code. Here's an example demonstrating the creation of a custom iterator. We define a template class named myIterator that represents our custom iterator. Within the class, we define the iterator category as forward iterator tag, indicating that our iterator supports forward traversal. We also define the value type, reference type, pointer type, and difference type for our iterator. We then implement the required operations, such as the pre-increment operator, the dereference operator, and the equality operator, to provide the necessary functionality for our iterator. To ensure efficient and reliable code when working with iterators, consider the following best practices. Prefer standard algorithms over manual loops whenever possible, as they are often optimized, thoroughly tested, and clearly express your intent. Utilize range-based for loops for simple traversal tasks, as they offer improved readability and reduced risk of errors compared to explicit iterator loops. Be mindful of operations that may invalidate iterators, and refresh iterators after container modifications to prevent undefined behavior. Always verify that an iterator is not equal to the end iterator before dereferencing it, as dereferencing the end iterator can lead to crashes or unexpected results. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.